So Algebra 2, 2.8, this is the end of our chapter. Today we're talking about absolute values. So absolute value, basic reminder of absolute value, is those bars. So if I stick -7 in there, you'd shoot me back a 7. If I put +7 in there, you'd still shoot me back a 7. Okay, absolute value is often defined as it's the distance from 0. Sometimes people will tell you absolute value is always positive. It's not exactly true because the absolute value of 0 is 0, and 0 is not positive. It would be more accurate, completely accurate, to say absolute value is non-negative. You can't get negatives out of absolute values. You do usually get positives, but you can get 0, and 0 is in a club of its own. All books at some point will give you this definition for absolute value. So it's a whole lot of complicated math formula, symbol things, but it's just telling you to do the absolute value of a number. You can just keep that number the same if that number is greater than 0 or if it's equal 0. In other words, if I do the absolute value of 0, leave it alone. I do the absolute value of a positive, leave it alone. Second option, if I do the absolute value for a number that's under 0, in other words, a negative number, this means to change the sign. So this is saying to do the absolute value of a number, drop the bars if that number is positive or if it equals 0. Change the sign if that number is negative. That's what that's about. The first thing the homework's going to ask you to do will be a new thing you've never done with absolute values before, which is to simplify absolute values. The goal there is to leave as little inside those bars as possible. If you have something that for sure is positive, or 0 already, you don't need the bars. You can drop them. So there's 3 rules at work here. One is if you have a multiplication problem inside of bars, you could separate that to 2 different little mini bar problems, each in their own set of absolute values. I'll take a stroll to the right to show you that and how that works to simplify. So this, I have multiplication in the bars. I could do the 5 in its own little problem. I could do the x in its own little problem. And then I could think about whether I could do those problems. I can do this one. The absolute value of 5 is 5. The absolute value of a variable, that's a little bit mysterious. You don't know if the variable is positive, negative, 0, what it is. You can't really touch that. This is considered a simpler answer than this because there's less stuff in the bars. So that's one rule we can work. Another rule we can work is the same with division. If you have a division problem in the bars, you could make 2 separate little mini bar problems where the dividing is in a separate part of this. So here's a division part of that. -7 could get its own little piece. Y could get its own little piece. The variable is too mysterious to really do much with it. Just leave it alone. But the absolute value of -7 is 7. This is considered simpler because, again, there's less stuff in the bars. We also disappeared a -7. Third rule we have is involving powers. Anytime a number goes to a power, if that power is even, you know it can't be negative anymore. So if you have absolute values surrounding a number that's to an even power, you can completely drop the bars. So with something like x to the 4th, you know that that can't be negative. The bars really have no value to us. Drop the bars, that's considered simpler for sure. For something like this, the easiest one to attack is the z to the 8th. Because that's an even power, we don't need the bars at all for z to the 8th. Y to the 7th is odd, so that creates a little bit of a dilemma. You don't really know whether odd powers go negative or positive or what they do. A negative to an odd is negative. A positive to an odd is positive. 0 to an odd is 0. That could go any which way. But what we can do is realize with y to the 7th, there would be safety in y to the 6th. It's only that extra 7th y that's causing us uncertainty. So what we want to do is pull out these bars as much as we can take as much even out. With z to the 8th, take it all out. With y to the 7th, you can pull out an even 6, just leave an oddball underneath. With x cubed, pull out x squared, which is the largest even, under 3. And since it's odd, you just have to leave a single x in there. For a problem like this, the negative 3 could turn into a positive 3, just like we had the negative 7 became a positive 7, the regular 5 was a regular 5. With x to the 7, we can pull out the even amount of 6, but you're stuck leaving a single x in the bars. Long story short, every time there's an odd power, leave one of that letter in, but pull out every even amount you can pull out every time. So this fraction one, the absolute value of negative 3 we can do, it's 3. X to an even, we can just drop the bars entirely. Absolute value of 5 is 5. Y to the 7th is a little bit of hassle. It's an odd, so we have to leave 1 in, but you can pull 6 of them out. And this is considered simpler because there's way less stuff in the bars than there used to be. This isn't life-changing or gigantically important, but it's a thing. Second thing the homework will do is ask you to find distances between some coordinates on the number line. The coordinates are numbers on the number line. One thing to realize about distance is always defined as positive. So if I ask you the distance from here to New Ken and it's 8 miles, and I ask you the distance from New Ken to here, it's still 8 miles. It's not like it's 8 miles one way and negative 8 the other way or something. So if they ask you the distance between two coordinates on the number line, you're going to subtract the coordinates in any order you want to. But when you're done, if you turn up with a negative, just erase it. And that's essentially what absolute values do, is erase negatives. So that's why this gets thrown into this lesson. So if we want to know the distance from negative 3 to 2, you could either go negative 3 minus 2, which is negative 5, to make a final answer of positive 5 by switching the sign. Or if you subtract in the other order, 2 minus negative 3, minus minus is plus, it's still 5. Okay, so bottom line on these distance questions, subtract the numbers whatever order you want to. Just make sure your answer is positive. So if somebody wants to go distance from negative 3 to negative 11 by doing negative 3 minus minus 11, and somebody else wants to go negative 11 minus negative 3, you're both on a fine road to be right. Make that a plus, you get an 8. Make this a plus, you temporarily get a negative 8, but since we have to be positives, the final answer is going to be 8 either way. That's not gigantically important either. The thing you're most likely to see again on SATs, calculus class, other times this year, other things, is solving absolute values that have either equals or graders or lesses. So if we try to think about the number line, think about and then pause and then see if you're right. Where on the number line do you have a number or some numbers that have absolute values that are 7? Contemplate that, pause it, return. There's 2 places on the number line that the absolute value of x could be 7. 7 itself, or negative 7. The absolute value of 7 stays 7. The absolute value of negative 7 becomes 7. Anytime you have an absolute value equation, you're going to get double answers. Something to equal the positive version of the number, or something to equal the negative version of the number. So let's do this one. If I want to solve this equation, I'm going to get a double answer. The 6x minus 5 is going to be part of both answers. Copy this exactly as it is. This thing could equal 7. This same thing could also equal negative 7. These are both completely accurate answers. I'll just throw the word or in there. We can do one or the other. If there's a 7 in here, we're going to win. If there's a negative 7 in there, the bars would make it a 7. So it's double answer time. We want to add 5 and then divide by 2. And as always, you can plug your answers in to check. 6 times 2 is 12, minus 5 is 7. The bars keep that 7. That's a win. If we solve this, add 5 to get negative 2. Divide by 6 to get a negative 1/3. If you want to check this, 6 times negative 1/3 would be negative 2. minus 5 would be a negative 7. The bars would turn it into 7. You'll always get a double answer off these absolute value equations. If I go back to here and ask you to find places that the absolute value is more than 7, think that over. Check back in when you unpause in a minute. If we're looking for places on the board or on the number line where the absolute value is bigger than 7, there's two locations. Everything from 7 and up, 7, 8, 9, 10, 11, 12, the right end of the number line would do that. Anywhere that x is greater than 7. Or if you went all the way to the left end of the number line, negative 8, negative 9, negative 10, all those negative same numbers, once you did the bars, they beat 7 as well. So x could be more than 7, or x could be less than negative 7. And that kind of establishes a pattern that you could do any greater than problem with. Whatever's in the bars will get doubles. Greater than 7 once, less than negative 7 in the other zone. So we can do this problem that way. 4x plus 2 doubles. Greater than 7 in one world, less than negative 7 in the other world. Throw an or in there and go at it. Subtract 2 to get 5. Divide 4 to get 5/4. Over here, subtract 2 to get negative 9. Divide 4 to get a fraction, negative 9/4. Last option is less than. Think about where on the number line do you get absolute values under 7. Pause it, think it over, come back. Places on the number line where the absolute values are under 7, it would be like 6, 5, 4, 3, 2, 1, 0 stuff. But then even into the negatives, negative 1, 2, 3, 4, 5, 6 kind of stuff. Those all have absolute values that stay under 7. But you can't get too high, like 10, that's too big. You can't go as low as like negative 10, because the bars turn that into 10, and that's then too big. We'd have to stay with our x between negative 7 and 7, and our less than sandwich is back. Absolute values with a less than, copy in the middle the thing you're given in your less than sandwich, and then these numbers, positive versus negative, fill in that gap. So if I want to solve this, I copy 3x minus 6. Anything less than, I'll go less than sandwich. With 7s, I'll go high end 7, low end negative 7. If I add 6, this end is up to 13, this end is up to negative 1. This, I go up to 13/3. This, I'd be at negative 1/3, and we're good. Then here's 3 what ifs. So if I go back to these and I decide to go negative on these, it totally changes the game. These are 3 weird misfit problems. Think them over, come back, and see if you can decide when are these sentences true. An absolute value to equal a negative, an absolute value to be more than a negative, an absolute value to be less than a negative, and try to contemplate that. When you return, I'll talk. For an absolute value to ever equal a negative is impossible. Okay, these bars, it'll keep 0 as 0, it'll make everything else positive. Absolute value could never equal a negative. There would be no answer to that. That's the symbol for I can't do this, this is impossible. If you didn't have that, pause, rethink. One of these two is also impossible. It just can't happen. So you can check back with me in a second. And it is this one. Absolute value can't equal a negative. Absolute value certainly can't be under a negative. Okay? Again, absolute value would keep 0 as 0. It would make negatives into positives. There's no way that this number right here could be less than a negative. This can only be 0 and up. So that's an impossibility. There's no way that can happen. This is a different kind of misfit. How often is absolute value more than a negative? That answer is always. This is a fancy math symbol that means always. That fancy R stands for all real numbers. The real numbers we did, I think, on day one, that's all the numbers you know. If I give you something that's always true, that's an okay symbol for that. It's not a regular R. I did a double line to start my R, and then made an R out of that double line, and that just stands for all real numbers. You could also do that on problems like if I said x plus 2 less than x plus 3, solve that. What makes that true? Literally everything. Because if you tried to solve this, if you wanted to get rid of one of the variables, subtracting an x on one side subtracts the x on the other side, in your experiences, how often is 2 less than 3? I'd say always. You know, this is, again, similar. Always. Regardless of what x's you would try to use in this story, that would always just work out. That's it for this. Homework is 88. Yes, 88. 88, we're working from 2 to 40, evens only. And that's a wrap on our chapter. We'll gear up on some reviews and some quizzes and reviews and tests in our near future.